Chapter 4, Probability, Section 4.3, the addition rule. This section in particular, you want to see your textbook and of course the homework problems for examples. I will be using some of the homework problems and also a few examples from a deck of cards. First of all, the key concept is that the addition rule is for finding probabilities of one event or another event. Probability of A or B, the probability that either A occurs or event B occurs or they both occur. It's always the inclusive or, one or the other or both. A compound event in general is any event combining two or more simple events. This is an example. We'll also look at the probability of A and B, A and then B, and A given B. This is the probability of A or B. The nice thing about this situation is that you're talking about a single trial. When we get to the multiplication rule, you'll be looking at A happening and then B happening, which is two trials going on. The formal addition rule says the probability of A or B is the sum, hence the name, addition rule, of probability of A plus probability of B, but you have to subtract off the probability that they both happen at the same time. Basically, the intuitive idea is to find the number of ways that A can occur and the number of ways that B can occur, but you don't want to add anything twice. So if you add the probabilities separately, if they can happen at the same time, you have to subtract off that possibility. There's the difference between whether events are disjoint or not, also known as mutually exclusive events, whether they overlap or not. In a deck of cards, for example, you can have one event being selecting a king out of a deck of cards. There's 4 kings. You could have another event being selecting a heart out of a deck of cards. There's 13 hearts, but there's one card that's both, the king of hearts. So those would be not disjoint, not mutually exclusive. An example from a deck of cards of 2 events that are mutually exclusive would be getting a king and maybe getting a queen, because there's no card that's both a king and a queen at the same time. Those are separate, disjoint, mutually exclusive from each other. And the addition rule is different depending on which situation you're in. Another example of disjoint events is complementary events. The notation A with a bar over it is that A did not happen, and an event and its complement, A and not A, must be disjoint. You can't have an event happen and not happen at the same time. It's like it's either raining or it's not raining. And so they're related by the addition rule. The probability that it rains plus the probability that it doesn't rain is 100%. And this can be handy for finding the probability that an event doesn't happen by subtracting the probability that it does happen from 1 or 100%. For example, what's the probability that it doesn't rain if the probability of rain is 20%? Well, 100% minus 20%, or 1 minus 0.2 is 0.8. So there'd be an 80% chance that it doesn't rain. And it works both ways. Here's a Venn diagram showing that situation here. The probability of an event is the yellow circle, for example, probability of rain, and then the squares is the total 100% probability, either it rains or it doesn't. Here's an example from a deck of cards. So probability of king, getting a king, when you pick a card, is the number of kings, 4 kings, out of the total number of cards. That's what we call your sample space. So 4 out of 52, which reduces to 1/13, or if you divide, you get decimal. The probability of getting a heart when you pick a card out of a deck of cards is 13 out of 52 because there's 13 hearts out of 52 cards. That reduces to 1/4 as a decimal is 0.25. So then we look at the compound probability. What's the probability that you get a heart or a king or both? Well, there's 13 hearts and there's 4 kings, but there's that one king of hearts out of the 52 cards. So there's actually 16 different cards out of the 52 cards that are a king or a heart or both. So that's 4/13 or 0.308, about a 30% chance. Again, notice that those are not disjoint, whereas the probability of king or queen is a little simpler situation because there's 4 kings and 4 queens, and so you just add them together. 8 cards out of 52 is the probability of getting either a king or a queen. Now from the homework, let me go to my stat lab and show you some problems, examples of using the addition rule with contingency tables. Example or question 7 has a contingency table for some drug testing. We've got some subjects that use drugs and some that don't use drugs, and this test that is not very accurate gives them either a positive test result or a negative test result. So we have 87 drug users that got a positive test result. That was an accurate test. And then 4 drug users that got a negative test. That's called a false negative. And then we've got 82 non-drug users that got a positive test result. So those poor people got a false positive and are going to have to be retested to clear the fact that they don't use drugs. Fortunately, 827 of them got the accurate test result of a negative test. So now this question is actually more simple maybe than it looks at first glance. What's the probability that a subject either had a positive test or a negative test? It's not asking anything about whether they're a drug user or not. So technically you would look at how many got a positive test out of the total, which they said is 1,000, and how many got a negative test out of the total, and add them together. Those are disjoint events. They either had a positive or a negative test, but they are also complementary. So this one has a very easy answer. It is 100%. So you could use the addition rule, but you'd basically be adding 169 out of 1,000 to 831, adding those together out of 1,000, and you get 1,000 out of 1,000. Let's look at the next one. This is a contingency table of a bunch of accidents, 946 pedestrian deaths that were caused by accidents. And in some cases the pedestrian was intoxicated, and in cases the pedestrian was not intoxicated. In some cases the driver was intoxicated, in some cases not. Now the probability that the pedestrian was intoxicated or the driver was intoxicated or both is going to involve the addition rule. And notice that these are not disjoint. They are not mutually exclusive. There were 60 cases where they were both intoxicated. Let me show you a trick here. There's a little icon where we can open this in Excel, and I can use Excel as a calculator. Of course, you can write this down and you can use your calculator. I am going to open this in Excel. Okay, so here it is in Excel, and there's a nice trick in Excel called an auto sum feature. You might remember that the capital Greek sigma means sum. If you click on the cell below a column of numbers and hit that button, it will automatically add those two numbers. And you can hit enter. Over here I want to add those numbers. Enter. And should be able to do this over here as well. It should know that you want to add, in fact, those rows. And here. And then let's see if we can make it add the that column or that row should give the same thing. Actually, that is not correct. Let's see what's going on here. If we add, yeah, we want to add these guys. All right, that should fix it. So 946 is the total. All right, so now I can use this as a calculator. If you hit equals when you type in Excel, it treats it as a calculator. So for example, the probability that the pedestrian is intoxicated is equal to the number of pedestrians that were intoxicated, 352, out of the total accidents, 946. And then I want to add that to the number of cases where the driver was intoxicated. So that's 154, or the probability, I should say, of the driver being intoxicated, which would be the 154 out of the 946. But then here's where we need to realize that those events are not mutually exclusive, and these 60 cases here where they were both intoxicated just got counted twice, because that 60 is in that 352, and that 60 is in the 154. So what we need to do is subtract the 60 out of 946. And that gives us the probability that one or the other or both. Now this is not a very complicated contingency table, so we could do it without the sums and actually just take the numbers of people from the inside of the table, the 60 people that were killed when both were intoxicated, plus the 292 where the pedestrian was intoxicated but the driver was not, plus the 94 cases where the driver was intoxicated but the pedestrian was not. And that whole thing over the total divided by 946 would be another way to use the addition rule to get the probability of one or the other or both. So either way, 0.471 to 3 decimal places, which is usually what they want. All right, let's do one more. This one is asking about labels of drugs and whether physicians made the correct dosage or not based on the labeling, ratio label or concentration label, and whether they made the correct dosage calculation or not. This physician, this is the probability the physician made a correct dosage or was given the bottle with a concentration label. So that again is a situation where we need to add. Let me see if I can get this to open in Excel. Okay, here we go. These numbers are nice and small, so it's actually pretty easy just to do this in your head if you think about it, except for getting the final decimal. So the question again is, what's the probability that the physician made a correct dosage, so this column, or was given the bottle with a concentration label? So that would be this row. So that means we want to add the correct dosage column to the concentration label row, but not add those 12 twice. So again, we can add 2 plus 12 plus 4 and get 18 and divide that by the total, which is 28. They in fact told us it was 28. So 2 plus 12 plus 4, let me show it to you here, equals parenthesis 2 plus 12 plus 4 divided by 28. And the probability is 0.643.